So welcome. In the previous lecture, what we have seen is how do we characterize plug flow, how do we characterize well mixed behavior, what conditions are required which will ensure that we get plug flow or which will ensure that we will get well mixed. In this lecture we are going to continue this concept further, and first of all what we are going to look at is what are the mathematical ways in which we characterize well mixed behavior, what are the mathematical ways in which we characterize plug flow behavior. Okay, and then we will go forward and then we'll go to reactors which don't behave like well mixed or plug flow. So let's just get started, and before we get into this lecture, let me just quickly tell you where we are in the course. We are in this point number 3, third part of our course, and just to help you quickly revise, you can list out this in your notebooks. What conditions are required to be satisfied to get a plug flow behavior? What conditions are required to be satisfied to get a well mixed behavior? And I would like you to derive equation for balance of A on a differential control volume which considers convection, dispersion, turbulent dispersion, and reaction of A inside this control volume. And then using that equation, how do we think in terms of the conditions required to get plug flow behavior, what conditions are required to get well mixed behavior. We have also seen this chart at the end of the lecture that using this equation you can either measure and solve the partial differential equation, or you can predict and solve, that's called as computational fluid dynamics, or we can experimentally measure how the reactor responds and we can compare the response of the reactor to a plug flow behavior and compare the response of the reactor to well mixed behavior. Okay. So first of all, what we are going to do in this course is what is the response of a plug flow reactor to a stimulus, and what is the response of a well mixed reactor to the stimulus. And once we know how these so-called idealized reactors behave, then we would be in a position to compare the response of a real reactor and say, this real reactor behaves like plug flow, or oh no, this reactor behaves like a well mixed behavior, or no, it does not behave like well mixed, it does not behave like plug flow, it behaves something in between, and then we'll have to do something more to characterize the response of that reactor. Okay, and design such a reactor or analyze such a reactor and improve the performance of such a reactor. Okay, let's go forward. Okay, so first of all, we are going to look at a well mixed reactor. Again, so well mixed reactor means this is the reactor, concentration everywhere is the same. What we are going to do is we are going to put a tracer, which means it is not a reacting species, it is something which we can measure. We will call that as a tracer, and we'll put this tracer as a pulse. What I mean by pulse is we'll put one shot of that tracer into the reactor through the inlet, just one shot, and very quickly we are going to put that shot. Okay? And we are going to record the response of the detector, if you like, or we are going to measure the response, measure the concentration of this tracer at the outlet. Okay? So this is where we put in this tracer as a pulse at t equal to 0, and after we continue measuring at the outlet the concentration of the tracer, we get a response something like this. It can be like this, it can be something else. We will calculate that. So what I would like you to do is derive an equation for the outlet concentration of this tracer as a function of time. Your reactor is operating at steady state, but the tracer is a one shot, it is unsteady state with respect to the tracer. We try to understand, reactor is operating at steady state, but tracer is put in at one time, and we want to find out how concentration changes with respect to time. It is a dynamic behavior with respect to the tracer. With respect to the reactant that may be coming in, it will be a steady state behavior. Okay, so let's say m moles of the tracer are put in at time t equal to 0, and mixing is very rapid. That means all these m moles completely mix inside this reactor at time t equal to 0 instantaneously. So what I would like you to do is derive concentration or outlet concentration of the tracer as a function of time, and use that to derive expressions for residence time distribution and variance sigma square. You've done this in your undergraduate course, okay, but we are just trying to revise. Some concepts may or may not have been very clear in your undergraduate course. That's why we are doing them now. So pause the video, do this for yourself, then only go forward. Okay, here is what you will get. At time t equal to 0, if m moles are put in and instantaneously mix, concentration of the tracer at time t equal to 0 would be m divided by v. Now, material balance, unsteady state material balance for the tracer. This is unsteady state material balance for the tracer. Not with respect to reactant. With respect to reactant, it is at steady state. Tracer is dynamically put. It is unsteady state with respect to the tracer, for the tracer. So accumulation Vc at time t plus delta t minus Vc at time t would be inlet is 0. Okay. Why? Because tracer is only put in at time t equal to 0. No other time tracer is put in. Tracer is not there at any point t greater than 0. There is no tracer that is coming in for t greater than 0. Okay, so entry is 0, in is 0. Out is flow rate concentration multiplied by delta t. So this is with respect to this, we are writing this balance, material balance for the tracer. Okay, and minus dc by dt, if you do, we'll get c by t tau. And if you integrate and put a condition that at t equal to 0, c is ct at t equal to 0. Initial concentration of the tracer, initial in the sense at t equal to 0. And you'll find that ct is c at t equal to 0 e raised to minus t by tau. This is how the tracer concentration will change with respect to time. Just plot this. If at t equal to 0, this is our t equal to 0, that is where we have put in the tracer. What tracer we have put in? We have put in as a pulse, which means one shot of tracer. Okay. Outlet concentration will change like this, exponential behavior. Concentration versus time, concentration at the outlet versus time. Okay. This behavior, this is that equation. Okay. This would be concentration of the tracer at time t equal to 0. It is m by v. Okay. Derive this for yourself, then only go forward. Pause. Okay. What is the total moles of the tracer coming out? 0 to infinity, flow rate multiplied by concentration multiplied by dt. Concentration kilomoles per meter cube if you like, flow rate meter cube per second, rate at which it comes out, integrated with respect to time from 0 time to infinite time. Every time 0 time to infinite time, all tracer is all coming out here. When we say E curve, what we mean is how much tracer comes out as a fraction of the total, right? If you want to think, you can think at any time t, what is the flow rate that comes out, or what is the tracer? A flow rate is f, what is the tracer that comes out? It is ct. As a fraction of the total, f into c dt integrated from 0 to infinity. This f just cancels. So that's why we had used this definition in our undergraduate course. So et into dt will tell you how much fraction comes out at this small interval dt. If you think about this small interval dt, if you think about a small interval dt here, flow rate multiplied by this concentration into this dt, that is what has come out in an interval of time dt. And if I add up all such intervals of time dt, I should get it as 1, because that should be the total mass of the tracer or total moles of the tracer. Okay. So ET, our definition of ET is going to, well, let's put some color, same color, black color we don't want. ET is C at time t divided by integral 0 to infinity C at any time t dt integrated over this whole time. Okay. And integral 0 to infinity et dt, this is 1. Why? Because et dt tells you how much fraction of the tracer comes in during this interval dt at time t. So obviously all such fractions added must be equal to the total 1. Fractions add up, everything becomes 1. So mean residence time we can define as weighted average of this ET, time weighted average, statistics, right? So it is time weighted. That's what is the meaning of mean, time weighted. It is weighted with respect to time, statistics. Okay. So tau would be integral 0 to infinity t et dt. So recall, units of et would have 1 per time, 1 per second, 1 per minute, second inverse, minute inverse, right? That would be the hour inverse. That would be the units of et. And et dt represents fraction of the tracer coming out at time t in an interval dt. Right? You've done this in your undergraduate course, but think about all these things because now we have to start using all these. What is the variance? Statistics. What is the variance of this distribution? Variance is integral 0 to infinity t minus tau the whole square et dt. So if you substitute for this et, it will be t minus tau the whole square 1 by tau e raised to minus t by tau integrated with respect to t from the interval 0 to infinity. And you will find that sigma square is equal to tau square. You don't just take my word for it. Do integration yourself and prove that you get this. Okay. Prove it for yourself. Only then you will be able to understand, only then you will be able to appreciate all these things. Why we require variance. Okay. Okay. We could write in terms of, so if this is in terms of actual time domain, but we could write in terms of dimensionless numbers. Why? Because then we can do it for any other reactor as well. So we could define dimensionless parameters. We could define a dimensionless time. So this theta is dimensionless time. Right? Is t by tau. And our E curve now, Et would be 1 by tau e raised to minus t by tau. So this t by tau will become e raised to minus theta. And then I can bring this tau here. Tau Et we would call as dimensionless E curve. Similarly, sigma square 0 to infinity t minus tau the whole square Et. We can divide by tau, multiply by tau square 1 by tau e raised to minus t by tau. Right? So this will become theta minus 1 the whole square e theta. E theta, this is our E theta. 1 tau will get cancelled, right? And it will become tau dt. But this t also we can represent from this expression. It will become dt would be tau d theta. So now if you write that, it will become tau 0 to infinity tau square theta minus 1 the whole square e theta d theta. So this is our dimensionless variance. And how we will get that? Is bring the tau on the other side. So sigma theta square, this is our dimensionless variance. Would be sigma square by tau square. Would be 0 to infinity theta minus 1 the whole square e theta d theta. Okay. So do this for yourself. Okay, understand this derivation. it's easier to think in terms of dimensionless numbers, dimensionless parameters, because we might be wanting to compare different reactors having different residence time. Okay, then we can compare on the basis of these dimensionless numbers. Okay, let's go forward. Now, one way of doing a response, so when you had done your undergraduate course, you must have done dynamics of, let's say, first order tank or a first order thermometer or interacting tanks, non-interacting tanks, right? It is the same here. Only thing is we are seeing the dynamics with respect to the concentration of the tracer. That's why we want to see mixing behavior. That is, its dynamics with respect to how it is getting mixed. So one way of doing dynamics is to put a pulse, a pulse, which means we put all the tracer at one point of time. We call that as a pulse of tracer. One shot, you put all the tracer. Or second option could be to do it as a step change. Step change. Where is that? Let me write that somewhere. Step change. That means tracer concentration, let's say it was 0 initially, we increase the tracer concentration to some value, let's say Ci, and keep that tracer concentration at Ci throughout time t greater than 0. So this looks like a step in a staircase, right? So therefore it is called as a step change. You gave this step change for flow rate, and when you had studied dynamics of a tank, you gave a step change with respect to temperature when we were studying dynamics of thermometer. You gave a step change in the inlet flow rate when you wanted to study dynamics of two tanks, interacting tanks or non-interacting tanks, right? So ultimately this outlet concentration, if I measure with respect to time, outlet concentration will increase and ultimately it will become equal to this Ci, inlet concentration. Again I am emphasizing, a reactor is operating at steady state with respect to the reactant. Reactant might be coming in at flow rate, Ca, and so on. Tracer is what we are doing dynamically. We want to see dynamics of tracer. So it is unsteady state with respect to tracer. With respect to reactant, it is at steady state. Okay. So now I want you to derive an equation for outlet concentration as a function of time for the step change. That will be called as F curve. Okay. And then using this F curve, we can derive our E curve. Pause the video, solve it for yourself. Okay, here is the solution. If you have not done it, pause. Do it for yourself. Only then go forward. These lectures are not to be seen just like that. You have to solve. That's why 1 hour lecture may take you 3 or 4 hours to understand and do all the homework. Okay, so step change. Again, we can do in minus out is equal to accumulation. What comes in minus what goes out. In minus out would be accumulation. Accumulation would be V, D, concentration of the tracer at the outlet divided by dt. Simplify. Okay, boundary condition at t equal to 0, concentration at the outlet is 0. Outlet is 0. Right? T equal to 0. Oh, sorry, t equal to 0. Nothing is there at outlet. Simplify. C out will be Ci divided by 1 minus e raised to minus t by tau. So the F curve is how a dimensionless outlet concentration changes. So that F curve will be nothing but Co by Ci, because Co at the outlet is going to change from 0 to Ci. Dimensionless outlet concentration is C0 by Ci, C out by Ci. Right? That is called as our F curve. So F curve would be 1 minus e raised to minus t by tau. If I differentiate this F curve, what do I get? Derivative with respect to time of 1, that's 0, minus derivative of e raised to minus t by tau is e raised to minus t by tau and minus 1 by tau. So if you simplify this, df by dt would be 1 by tau e raised to minus t by tau, and that's nothing but our E curve. So our F curve and E curve we can relate to each other. Derivative of the F curve, time derivative of the F curve is nothing but our E curve, right? So we can get the F curve by step change. Step change gives us the F curve. Pulse input of the tracer gives us directly the E curve. So sometimes it is easier, actually when you're doing an experiment, it is much easier to do a pulse, but mathematically if you are analyzing, it becomes much more easier to do a step change because you don't have to describe mathematically the pulse of the tracer. So that's how these two ways are there in which we can see the response of a reactor. So a well mixed reactor will have a response ET equal to 1 by tau e raised to minus t by tau or E theta equal to e raised to minus theta. So if there is a reactor, industrial reactor, and we do a step change or we do a pulse input of tracer and we find that reactor behaves like this, then we can say that our real life reactor behaves like a well mixed reactor. So that's why we studied how a well mixed reactor behaves first, so that when we do an actual reactor, when we do an experiment on an actual reactor, we will know whether actual reactor behaves like a well mixed reactor or not. Let's go forward. Response of a plug flow now. So if there is no mixing, it is becoming like a piston. Our tracer that we have put in, this is our tracer that we have put in, the tracer will just come out in exactly the same way, but it will just be delayed by time equal to residence time in the reactor. So called delayed. It is just coming out after it has spent time tau. That's why it is called just a delay time. Delay, that word is coming from dynamics, process control, process response of different equipment, right? Transient response. So that's why it is called as delayed. Okay, but it's not delayed as such. It is just coming as a function of at a different time tau. So when you want to do an RTD experiment, what are the things that you should be doing? First of all, the tracer should be inert and non-reactive at the conditions. Your reactor may be operating at, say, let's say a couple of 100 degrees centigrade, 20 bar pressure, but the tracer should not degrade. The tracer should not react under the conditions of the reactor. Tracer should be miscible with what is being investigated. If you are investigating how the liquid phase is, whether it is behaving like plug flow or well mixed, then the tracer has to behave like the liquid phase, which means the tracer has to be miscible with the liquid phase. Its physicochemical property should not change. It should not vaporize at the reactor conditions. It should be easy to detect. Then only it is easy to measure the response or measure the concentration as a function of time. When you do an experiment, first thing to check is to do a material balance. How much tracer we have put in? Have we put in 100 kg, 100 moles, 10 kgs, 1 kg? And how much tracer has come out? Material balance. If I put in 1 kg of tracer and I get 0.8 kg only at the outlet, that means tracer has either reacted or tracer has remained inside or tracer is stuck to the wall. It is adsorbed on the wall. Maybe there is a catalyst that is here. It is adsorbed on the catalyst. Something like that. Right? Only then our analysis will be proper if our material balance is proper. Then we might have to change the tracer so that it is not adsorbed. It is not stuck anywhere. There could be, so So we might put a tracer somewhere here, but it will take time for this tracer to travel from here to the entry of the reactor. So this time we have to account for. It is a delay. It is not a delay because of the reactor. It is a delay because of the pipelines. Same way our exit from the reactor is here, but this pipeline may be going somewhere else. This pipeline may be on third floor. It's not easy to put a detection instrument at that location. Maybe it is 2 meters from the ground. So we might be putting a detector at a place where it is accessible. So there is a delay in the tracer coming out of the reactor and coming into the tracer, coming into the detection location. This delay must be accounted for, right? This delay or lag is due to pipelines. That has to be accounted for because it is not because of the reactor. It is not representing the reactor response. It is reactor response plus this delay in the pipeline, plus this delay in the pipeline at the exit. Pulse is easier to do experimentally. Step change is easier to do mathematically. Now think about some tracers that you can use when it's an aqueous phase, when it's a water that is aqueous phase that is coming into the reactor. Or organic phase, there is a reactant in the organic phase, solvent, xylene, toluene, acetone, methanol, that kind of solvent. Or a gas phase, there is a gas liquid reaction and air is supplied or hydrogen is supplied. I want to see whether the hydrogen is well mixed, whether the air is well mixed. What kind of tracer we can use for gas phase? Think about these issues. What kind of tracer we would want? What kind of tracer in the gas phase will be inert, non-reactive? It will behave, it will be miscible, it will behave the same physical properties as that of the gas phase or the liquid phase or the organic phase or the aqueous phase, right? Think about all these. So choosing a tracer is a very careful exercise. Doing an RTD experiment is a very careful exercise. It has to be done very carefully. But having done that, you will know how the reactor behaves, whether it is behaving like a plug flow, like this, or whether it is behaving like well mixed, like this. Okay. Make sure that you have understood all the things that we have talked about so far. Make sure that you are able to derive all these equations. Make sure you have understood all these concepts, especially with respect to tracer requirements. And once you have understood, then only now go forward. What we will do is we will solve a small problem now. So here is a problem. There is an RTD study being conducted on an industrial equipment. Pulse of tracer is given at the inlet of the equipment. Concentration of the tracer at the outlet is measured as a function of time. This is how the outlet concentration as a function of time looks like. We are going to use this data at other problems later on. So make sure that you do this problem properly because it is going to be required in our subsequent lectures. I would like you to calculate, or I would like you to plot the E curve. I would like you to calculate the mean residence time. I would like you to calculate variance, dimensionless E curve, dimensionless variance, and compare with the plug flow and well mixed behavior. And tell us whether this reactor behaves like well mixed or plug flow or somewhere in between. Do this for yourself. Use a spreadsheet, Excel if you want, to do all these calculations. Pause the video, get your answer for yourself. Then only go forward. Once you have got the answer, then only go forward. Okay, here is the answer. Hint. Use a spreadsheet rather than doing manual calculations. Use trapezoidal rule even for uneven intervals. For better visualization, plot the data. So do it yourself. Only then go forward. Pause the video. Don't just see lecture as if it's some TV show. Do the calculations. Okay, here is the solution. So if you, these are just taken from spreadsheet, so time 0, 4, 6, 9 and so on, this is the concentration, that's what is given to us. I can do integration now, trapezoidal rule across these two. So CT dt over this interval, it will be half into 0 plus 1 into 4 minus 0. You will get this. Trapezoidal rule over this interval. Trapezoidal rule over this interval. Trapezoidal rule over this interval. Let me just tell you this interval. 8 plus 6, 14 divided by 2, 7 multiplied by 16 minus 15, 1 over this interval is here. Over this interval is here. So integral CT dt from 0 to infinity will be just addition of all of these, 2 plus 6 plus 19.5 plus 18 plus 36 plus 7 and so on. You will get integral CT dt 0 to infinity would be 126.9. So the E curve would be, now I can rub out this. E curve would be concentration at time t divided by integral 0 to infinity CT dt. So at time t equal to 4, E curve would be 1 divided by 126.9. 1 divided by 126.9. The value of E function at time 16 minutes would be 6 divided by 126.9. That's what the E curve will be. Okay, make sure that you get these values. TET dt. So take this product T, I can rub this now. TET, this is the product. T4 multiplied by 0.008, that will give you 0.032. That's the product T into ET. 11 multiplied by 0.079, that will give you 0.867. 20 multiplied by 0.024, there's round off obviously, but it will give you 0.47. 28 multiplied by 0.012. Now TET dt, so we have to integrate, do a trapezoidal rule between these 2 points, multiplied by dt you will get these, between these two multiplied by this you will get this, between these two multiplied by dt you will get this, and integral TET dt from 0 to infinity means addition of all of these, 0.063, 0.268, 1.206, 1.434 plus 13.6, all these added together you will get tau equal to 13.91. Same way now we can calculate t minus tau the whole square et, t minus tau the whole square et dt, and get sigma square 0 to infinity will be 36.85. So what are the units? Et has units of minute inverse. Tau has units of t et dt minutes. Sigma square has units of t minus tau the whole square et dt. It has units of minutes square. Theta, it is t divided by tau 13.91. 4 divided by 13.91 will give you 0.288. 16 divided by 13.91 will give you 1.150. That's our theta. E theta is tau et. 0.008 multiplied by 13.9, 0.119 and so on. So calculate theta and E theta. Okay. Do this for yourself. Make sure you get these values. Then only go forward. Now plot. Okay, this is how it will look like. ET versus T. These blue points are how your data will look like. 2 sigma if you plot, your mean if you plot, mean is tau 13.9. 2 sigma if you plot, it will be like this, plus sigma minus sigma plus sigma. In terms of dimensionless numbers, if you want to plot E theta versus theta, This will be theta equal to 1. That is our tau, theta equal to 1. Okay. Plus or minus 2 sigma theta if you plot. Minus sigma theta plus sigma theta, this interval. This tells you the spread. Right? Standard deviation tells you the spread. Statistics. Now what do you want to do? Compare with well mixed behavior, compare with plug flow behavior. So if you compare with ET versus T, if you compare with plug flow behavior, this is how ET versus T would have looked like for a plug flow, ideal plug flow. This is how ET versus T would have looked like for a well mixed behavior, ideal well mixed behavior. This is the actual response of the reactor. Now tell me whether reactor behaves like well mixed? No. Whether reactor behaves like plug flow? No. In terms of theta, if you want, E theta versus theta. This is how an ideal plug flow would have looked like, E theta versus theta. This is how E theta versus theta would have looked like for an ideal well mixed behavior. Now tell me, this is the real reactor, actual reactor. This is how the E theta versus theta is looking like. Is it behaving like a well mixed reactor? Is it behaving like a plug flow reactor? No, it's totally different. So now how do we analyze this reactor? How do we analyze this reactor? How do I predict conversion in this reactor? Can I make this reactor behave like a well mixed reactor? Can I make this reactor behave like a plug flow reactor? This is what we are going to do in our subsequent lectures, right? What we have seen is how do we characterize this non-ideal behavior, either in terms of velocities, you solve the partial differential equation, predict, you can measure or predict using computational fluid dynamics, and solve. We are not going to do these two in this course. Okay? We are not going to do this. So what we did instead, we did an experimental measurement to a real life reactor. We put a stimulus, means tracer, either as a pulse or as a step change. We compare with plug flow behavior. We compare with well mixed behavior. It doesn't behave either way. So now what do? We'll look at two different categories. We will look at whether reactor behaves like a nearly plug flow with a small deviation from plug flow, or whether it behaves like a well mixed or a small deviation from well mixed. So this behavior, nearly plug flow with a small deviation for plug flow, we call it as plug flow with dispersion, or it is called as dispersed plug flow model, or we will say that it behaves like, not like well mixed, but it behaves like a series of well mixed tanks. So that is one extreme. So this is one extreme that we are going to do. This is one extreme that we are going to do, series of well mixed tanks. This is the second extreme that we are going to do, plug flow with dispersion or dispersed plug flow model. Or we say what combination of ideal reactors will have the same response like this real reactor. What combination? Okay, what combination? This is the third thing that we are going to do. What combination of idealized reactors, plug flow and well mixed? Combination means sequence. It could be two plug flows in parallel, two well mixed in parallel, plug flow and well mixed in series. Right? So many combinations are possible. We'll talk about them as we go along. We call these as compartment models. It's a combination of idealized reactors. These are called as compartment models. This is what we are going to do in our subsequent lectures. Series of well mixed reactors, plug flow with dispersion, or a combination of idealized reactors, compartment models. These three things we are going to do in the next lecture, and we are going to do these three things with respect to this experimental observation on an actual reactor. So that's why this example we are going to come back again and again, and we are going to see these three things: series of well mixed reactors, plug flow with dispersion, compartment models. We are going to use these to see what combination, what behavior can be represented or can be fitted to explain our real reactor. This is what we are going to do in our subsequent lectures. So just to give you some homework, we are on chapter 4th edition, chapter 13. You can solve this problem P1319, or if you are following the 5th edition, it's in chapter 16. We'll stop the lecture here. This is what we are going to do: 1, series of well mixed tanks; 2, plug flow with dispersion, dispersed plug flow models; or 3, compartment models. And we'll see how we can represent our actual reactor using any of these three. This is what we are going to do in our subsequent lectures.